Okay, hello. My name is Elias Pastrana with ID of A01552395. And I'm gonna present today my experiment one that is about the Marriott bottle. Well, first, what do we need to use a Marriott bottle? Well, first we need a 3-liter plastic bottle soda, a sharp knife, and a lighter. So with the lighter, you can heat up the sharp knife to do the holes. You need 2 straws, a pair of scissors, glue, a ruler, a bucket, and a chronometer. Here in the image of the left, I show you how I made my Marriott bottle. And in the top, I have the first straw, which is like the pressure, atmospheric pressure tube. And then I have at the bottom the drain tube. Also, I have 3 levels, which means that the first level is the maximum level of water. The second level is the level where is the straw, and the third level is where is the straw of the drain bottle. After that, we have the ruler, which can help us to do some measures. And in the image of the right, I have the setup of how I did this experiment. After that, we had to do some measures. And here I have H, capital H, H, D, and capital D, which means that the capital D is the inside diameter of the bottle, which was equals to 11.8 centimeters. And then we have the diameter of the drain hole, which was 1/2 centimeters. And then the distance between the atmospheric pressure too, that is this one that is located in a vertical way. And the reference level, which is this one with the straw that is located as in the horizontal way, was of 12 centimeters. And finally, the max water level between the drain tube and the maximum water level was about 22.1 centimeters. But it is really important to use the meters, so we can have this in mirrors. After that, we fill the bottle 5 times, and each time we measure how was the height of the water level each 5 times. So we did this experiment 5 times. So we filled the bottle 5 times, and we took the measures, and we have it here in the table. And in this table, we have the delta between the average of the sample of the measures. And here I have the velocity in the bottle, which was the large area, and the velocity in the outlet, which was the small area that was the drain tube. And after that, I had some graphs. The first graph was represents the time over the average height, which means that over the time, the height of the water level was decreasing. And in the other hand, we have the time over the velocity of the outlet, which is evaluated in meters per second. And here it looks like it doesn't have like too much sense, because there are like some points that they are like the graphic. But as here we can see, this part is when the atmospheric pressure tube is under the water, immersed in the water. And in this part is when it is already above the water, and the velocity it starts to decrease. After that, we compared it with the theoretical results, which were these ones, and we calculate this by the square root of 2 times g times capital H. And it demonstrates that the theoretical result of the velocity of the outlet of the bottle of the drain tube, it should have been 1.547 meters per second. And also it is until the 30 seconds, which were the time that the atmospheric pressure tube was immersed in the water, and then the velocity starts to decrease. After that, we have the theoretical table, the graph, sorry, and this shows the time over the theoretical velocity out of the outlet of the drain tube, also measured in meters per second. And as we see, the how this is seen, that it is really horizontal, and after the tube is isn't immersed yet, it starts to decrease the velocity. What we can do for conclusion? That according to the average of the outlet velocities by the experimental method, while the atmospheric pressure tube is immersed in the water, it indicates that the water flows out of the bottle at a speed of 0.0116 meters per second with an uncertainty of 0.0004 meters per second, while the theoretical method indicates that the speed is 1.574 meters per second with an uncertainty of 0.003 meters per second. Thank you very much.